Alright guys, I figured out why my last video looks like a potato, so we won't hopefully look as bad this time around. Okay, so just in case, a few things. Some of you asked for the divider, so I'm going to post that if you want to add this. And oh my gosh, page numbers though. Page numbers are tough. Alright, the last page that we did was page 80. So on 81, we're going to have intro to radicals, which is, if you're able to print this sheet that we talked about last week, I'm going to add to that a little bit today. And then we also added some really good examples and how to simplify. So this will be, so this is 80. That'll be 81 and 82. Okay, so 80, 81, 82. And then that was simplifying radicals. Okay, so what we're going to talk about this week is multiplying and dividing radicals. So multiply and divide. But on the same page, next week we're going to talk about addition and subtraction. So I'm going to include them all on the same line, but this week we're only going to talk about multiplication, division. So multiply, divide, add, subtract radicals. Because whenever, like I said last time, whenever we have a new function, we got to talk about all of the things it's allowed to do and like how do we do simple math with a brand new function. So this will be on 83 and 84. Okay, so just in case you want to stay organized with me, I'm realizing that doing this from home, I am not as organized as I thought, but that's okay. So I got 81, 82 right here. These are the things that you'll find attached to this first video. We're not going to fill this all out on this one video, but kind of we have our book here, we have this one underneath here, and then operations on radicals with the cute little pictures on 83. So that would be 83. And then we got 84. And alright, so let's talk about the things. Like I said, I'm actually going to add a little bit to this first one here. So we kind of talked about the parts of a radical and like how we can simplify it, which you guys did a really nice job. I looked at a lot of your homework and it seemed like you were getting the idea, which is awesome. So now we're just going to up it a notch, because with multiplication and division, it's not much different than simplifying one of them. You usually just have more than one. There's just one small rule that you have to follow. So when we are multiplying or dividing roots, you can only multiply or divide roots that have the same index. And so I'm going to get into examples where they may not have the same index, but basically you do the outside number times the outside number, and then the inside number times the inside number. Or vice versa, like divide outside, so multiply or divide outside by outside, and inside the root you can multiply or divide. Obviously if something is outside, something is inside, you can't manipulate those numbers together, and hopefully that kind of makes sense. Now again, the roots have to be the same, so if I have two square roots I can do it, but if I have a square root and then a cube root, I can't do it. And in that case, you would just say already simplified and you're done. Okay, so I think the best way to do it is just try some examples. So in our little poof book right here, operations with radical expressions. Sorry, my allergies are so bad today. I had to wait forever because like I almost couldn't talk. I promise it's not the Rona. Okay, example 2 is the one we're going to jump to, because example 1's adding and subtracting. Do that next week. It's a little bit weirder. Okay, so when we're multiplying radical expressions, right across the top, guys, it tells us how we should do this. So again, as long as the index is the same, you can multiply the radicands, which is just that fancy word for inside number, together. You can also multiply their coefficients outside together and then simplify it after. Now the thing is, this suggests that we should simplify at the very end, and like looking at example 1, that I should multiply 18 and 27. Now, y'all don't like to use a calculator, and same. And I don't want to multiply that by hand, so I actually don't. I kind of just rewrite this as one big root, and I'm allowed to because they're both square roots, so it's all fine. And then what I do is I birthday cake each one. So I think about the 18, and if I were to birthday cake that, I can divide a 2 out, then I have 9, and then 3, and then 3, and then 3, and then birthday candle. And so the way that I can rewrite 18 is 3 times 3 times 2. Okay, so then we can do it with the 27 as well. And so I can take a 3 out of 27, we got 9, 3, 3, birthday candle. And so the 27, and again there's multiply in between these two, is 3 times 3 times 3. Now, underneath that root, I can make groups of 2 wherever I want. So I can group these 3's up, I can group those 3's up. I can't group up a 2 because there's not another buddy, and I can't group up that extra 3, so there's not another buddy. And so this 3 comes out, this 3 comes out. So a 3 and a 3 come out for 9. And then what I'm left with inside is still a 2 and a 3, and they're still being multiplied because all this stuff is being multiplied. So 6 is in. And that's your final answer. Okay, so it's really just like simplifying with extra steps. So it's like simplifying on crack because you just have to do it a ton. Okay, so we'll try another. So the 16, I know, is 2 times 2 times 2 times 2. And these are all under the cube root because they're both cube roots. So I can smash them both underneath 1. The 4, I can really only change that to 2 times 2. Now because we're doing a cube root, we're looking for groups of 3. So I have a group of 3, a group of 3, and so a 2 comes out and a 2 comes out for 4 because 2 times 2, and there's nothing left in, so no root left, so just 4. Alrighty, if we try this one right here, actually, you know, I'm going to skip 3 and maybe let you guys try that one. I think I'm going to do 4. I'm going to do 4 because the outside numbers. So because the 5 and 2 are already outside, I just push them to the front outside, and then I got my big old 4th root because again, like all the outside stuff can group together, all the inside stuff can group together. And so I know for now I have 10 outside, but then I want to break that 64 up, which 64 is 8 times 8. 8 is 2 times 2 times 2, and then another 8, so another 2 times 2 times 2. And then that 8, oh, that would have been easier, maybe 2 times 2 times 2. So, because we're taking a 4th root, I'm looking for groups of 4. So 1, 2, 3, 4, we got a group right there. And then 1, 2, 3, 4, we got a group right there. Oh, but one guy is left in. So a 2 is going to come out. Another 2 is going to come out, and like again, they're all being multiplied. So I have this 10 times 2. So 20 times 2, so 40 on the outside of my 4th root with a 2 left in. Now I do want to try one of the ones with letters as well because that might be kind of strange. So we have both square roots here, so we can smash everything underneath. And I can write these all out, but as Logan in first hour noticed, when you group them together, you're really just dividing. So because I'm taking a square root here, I can really just divide each of the exponents by 2 because the square root is 2. But I also want to put them under and like combine them. So as far as x's go, I can write out x squared times x to the 3rd, but if I have x squared and x to the 3rd, I really have x to the 5th. And then I only have one y because there are no y's in here. And then I have z to the 8th. And so I do multiply the letters because then it's easier for me to just divide. So again, because my root is 2, I'm going to divide by 2. So 2 goes into 5 evenly twice with 1 left over. So I will have a root with an x in it. 2 does not divide into 1 because it's y to the first, so the y is going to have to stay under. And then 2 goes into 8 4 times, so we'll have z to the 4th come outside, and kind of left a little bit too much space between them. No z's left in because I divided evenly, and there you go. I'm going to leave 5 for you guys to try as well. So 3 and 5. So that's just multiplication. We're going to jump to division as well. So that's the next example here. So like multiplication, as long as the index is the same, you can divide the radicands, which are just those inside numbers, and then simplify your radical expression. Now the fun thing is though, you can divide first if you want, so it's really up to you. Now the thing is, you have to have the same index. So looking at example 1, I can already tell, because this is the 4th root and this is the 7th root, I can't simplify those. The indices are different, so I would just write already simplified. But number 2's got the big old root around it, so definitely the same root on top and on bottom. So I can choose. I can divide the numbers now, or I can root it now. It's really up to me. Now the thing is, I don't know how to take the square root of 20, but I do know how to take the square root of 9, so maybe I want to leave the 20 and the 9. And then I think like, well, I can't divide 9 into 20, so maybe I will do it that way. So I'm going to leave the 20 on top and the 9 on bottom. But as far as the letters go, if I have x to the 3rd on top and x on bottom, then one of those can divide out and you're just left with x to the 2nd on top. Now I have y to the squared on top, but there's no y's on bottom, so y squared will stay. And on bottom, the x divided out here, but I still have z to the 3rd. So I divided a little bit. I divided what made sense with the letters, but I didn't divide the numbers because they don't really divide. So now I'm going to go through and square root. So I have to think about 20, and I'm going to birthday cake the 20. Let's see, what does 20 break up into? 2 times 2 times 5. So this is under my root. Then I got x squared, y squared over 9, z to the 3rd. And so now, because I'm taking a square root, I'm looking for groups of 2. So I have a group of 2 here, so a 2 can come out, but a 5's got to stay in. Oh my god, I'm going to run out of room. Let's just do this off to the side here on this paper. So 2 will come out, 5's got to stay in. Across the top, if I'm taking the square root of x to the 2nd, I'm really just dividing by 2. So 2 goes into 2 once, so 1x will come out. Same thing for the y, so no letters on top. Over on the bottom, the square root of 9 is just 3. And then the square root of z to the 3rd, well, is like divided by 2, so I can take one z out, but I'll have one z left in. And herein lies our very first problem, where we have to do what's called rationalize the denominator. That's what this last thing here is about. So we're going to jump down and talk about how we rationalize the denominator. Mathematicians are always like making up pesky little rules where they just want math to be written a certain way, and I guess it's so that everybody kind of understands how to read it. But one of mathematicians' pesky little rules is that you are not allowed to have roots in the denominator, which maybe you remember talking about in Algebra 1. So the process in which we get a root out of the denominator is called rationalizing the denominator. And since we're dealing with fractions or division, it's always okay to multiply a fraction by 1. It won't change the value. And any number or expression divided by itself is 1. So like x over x is 1, 2 over 2 is 1, x plus 2 over x plus 2 is 1. So to get rid of a root or a radical, in the denominator, we need to multiply the numerator and denominator by the root, or the radical, that is in the denominator. And then we simplified. So taking that example that I had up top there on number 2, we kind of finished the problem at 2xy root 5 over 3z root z. So the only issue is that I have this square root of z in the bottom here, and I can't have that. So what we said we were going to do is multiply by a fraction that is just a fancy looking 1. And the fancy looking 1 should be any expression divided by itself. And the thing that I want to pick is whatever radical is in the denominator. So we're just going to do root z over root z. And I kind of didn't make this big enough for this example, but that's okay. We'll just go up here. So it's really tempting to just cancel those out, but that kind of just gets rid of the thing that you needed. So really what you do here is you multiply across the top, across the bottom. So across the top, the 2xy just stays, but the 5 and the z are both under, so they can smash together under. On the bottom, we got this 3z outside, and now inside we'll have z times z, which is z squared, and now I can take the square root of that. So this becomes 2xy root 5z over 3z, but then the square root of z squared is another z, so this becomes to the second power. And then you don't have roots in the bottom anymore, which is super duper nice. Okay, so what I'm going to do is I'm going to jump up and do one more example from our proof book, and then I'll probably have you guys try some and check back with me Wednesday. So let's see. Let's do number 4. So number 4, we're taking the 4th root, and if you remember, the 4th root is kind of like square rooting twice. So I think about, can I take the square root of 81 twice? And if I take the square root of 81, it's 9, and the square root of 9 is 3, so I can do it. And I can also do it with the 16, because the square root of 16 is 4, and the square root of 4 is 2. So we'll have 3 over 2. And then I'm like, okay, with the letters, can 4 go evenly into the 4th power? And it does one time, so 1m comes out. And then does 4 go evenly into 8? And it does 2 times. And so no roots left, which is so very nice. Okay, so just a quick sum up, I would like for you guys to try 3 and 5. And then also on this page, let's try 3, 5, and 6. So in the next video on Wednesday, you guys will see me do those examples. We'll talk a little bit more about rationalizing, and good luck. Sorry, that was kind of a long one.